Good afternoon, everyone. I am Mr. Ish. Thank you for joining me for this video. We're talking about in this video integration using trigonometric substitution techniques. If you are cognizant of the fact that we have done polynomial substitution techniques, we've learned integration by parts, it makes sense that we evolve to this level of substitution techniques, the trigonometric substitution. You can basically break down the trigonometric substitution techniques into two forms of questions. You see the question form over here in the top row, the type of questions you're seeing. Contrast that sharply with the ones that you're seeing here in the bottom row. You have actual trigonometric functions here. Here you basically have polynomial functions, but these polynomial functions are disguised in the way that you would handle them using trigonometric techniques, which you will learn. These ones over here are generally more difficult than the type you see over here. These ones here on the bottom row are best handled using identities that you might be familiar with, and they all fall within the realm of trigonometric substitution. Some of these questions are actually, like of these sorts, are actually polynomial substitution techniques but disguised in the form of trigonometric substitution simply because we're dealing here with identities or trigonometric functions. Others like these here in the top row are a little more complex because you have to find trigonometric patterns within what you see over here and somehow convert this equation form or the integrand form into some form of a trigonometric identity or trigonometric function, and then from there you proceed with the substitution techniques. I want to spend some time at the beginning of this video looking at the easier types of questions, the trigonometric substitution forms, the integrals, like something which you would see in this form over here. And actually what I will do is these three questions over here, right here we see on the bottom, I'll start with those. Then we can see how we can progress to some of the questions of these forms. Keep in mind that within the realm of trigonometric substitution you have a wide range. You can go from something quite easy, something like this would be quite easy and this would be quite easy, to something which is slightly more difficult, like this would be slightly more difficult right over here, to something which can be even more difficult. Even by changing this right over here, we can make this question even more harder than what it appears by changing the sign over here, because we bring a different form of substitution techniques or different form of trigonometric function into play. So keep all of this in mind as you look through this video. Some of this can be hard, some of this can be easy, some of this will be just basic polynomial substitution techniques disguised under the topic of trigonometric substitution. Let's look over these ones first, the ones here in the lower row. Let's look over here. The integral of sine theta divided by cosine squared theta d theta. You can probably easily handle this using basic polynomial substitution technique simply by finding the one which is slightly more composite in nature and doing the substitution for that. This is one of those questions where you have a trigonometric substitution technique disguised within a basic polynomial substitution. So if u is equal to cosine theta, then du is equal to minus sine theta d theta, and you know d theta is equal to minus du divided by sine theta, and you would go with this form over here. And you'd come right over here and you'd do your substitution. You'd have sine theta on the top. In the bottom, u was representing cosine theta, therefore you see u square. D theta is represented by minus du. I'm bringing the minus over here, and du divided by sine theta. You know, these cancel out. You essentially just have minus, and you have du divided by u square. Not anything too hard, but this is still trigonometric substitution. Why? Because we're dealing with trigonometric functions here. You can bring the u square in the top. You'll have minus integral sine u to the minus 2 du, and then this is basically nothing more than polynomial integration over here. U to the minus 1 divided by minus 1, and you'll see how that is if you do it on your own in the paper. Minus 2 plus 1 divided by minus 2 plus 1, you get this. And then what do you get? U to the minus 1 plus c. When you take this to completion, you get cosine theta to the minus 1 plus c. And remember, this is not inverse cosine. What you get is 1 over cosine theta, right? Plus c, or you can say secant theta plus c. So this right here is your antiderivative for this question right over here. Let's just quickly show you that if you did the derivative of this, you'd actually end up with that, and I'll show you right over here. You're basically looking at the derivative of secant theta. You know, when you do the derivative of secant theta, you basically get secant theta tan theta, right? break these down into their basic functions. 1 over cosine theta times sine theta over cosine theta. When you open up all of this, you'll get sine theta divided by cosine squared theta, and you will have shown that the derivative of the antiderivative gives you back your original function, and that's exactly what you have. But this right here, for this question here, this right here is your antiderivative. Not a hard question, but this right here is trigonometric substitution, but you're using basically polynomial substitution here. It's kind of disguised within the question. And then you have questions of these types where you have an identity disguised within an integral question. You know, there's an identity which says that, let's put it right over here, sine 2x is equal to 2 sine x cosine x. You remember that identity. Well, you're pretty much seeing this, except you're seeing half of it. You can rewrite your entire integral like this. You're looking at sine x cosine x dx, but as an over 2, and you can make this over 2 right here outside, and you're basically looking at a question which is like this, because it's equal to something like this, and then you can rewrite everything as this. Your basic question type is sine 2x dx. That right there is this question using trigonometric identity converted into this form, and now you know this form is not any hard because you can use polynomial substitution and take it to completion. If u is equal to 2x, then du is equal to 2 dx, and dx is equal to du over 2. And you'll run with this part right here. You'll have 1 over 2, then you have sine u du over 2. These over 2's can come out as 1 over 4, and then you're looking at a sine u du, and you can take this to completion as minus 1 over 4, because the antiderivative of sine u is a minus cosine u, right? Cosine u, but what was u? U was this right here, 2x plus c. So we found right here, this right here, integrand gives you this as an antiderivative. You can take the derivative of this antiderivative and take it back to the original function, and I'll start by taking the minus 1 over 4 out, and we're looking at the derivative of cosine 2x, which you know you can use a chain rule over here. You have minus 1 over 4 d over du cosine u, and then du over dx 2x. When you open up all of this, you get minus 1 over 4 times 2x giving you the 2, and the cosine u giving you a minus sine u, which is a 2x. Bring everything together, what do you get? The minuses cancel out, the 2 over 4 becomes 1 over 2, you get sine 2x over 2. When you open up the numerator using a trigonometric identity, you get 2 sine x cosine x divided by 2. These 2's can cancel out, and you get sine x cosine x, and we're back to where we started right over here. So this right here is another form of a trigonometric substitution question, you can say, but it's not hard because this question relies on the fact that you have to convert your integrand into something more manageable using an identity, trigonometric identity. So you have questions of these types as well. You can see questions of these types as well. They're not hard, but they require a little bit more work to take to completion. If you're seeing something like that, then you want to start thinking about converting into something more manageable. And we're not talking about integrating by parts. You know, anything that's cube can be converted into this. Look at this, sine to the 1, exponent times sine to the square, exponent will give you that sine cube. Think about that Pythagorean trigonometric identity, and I'm talking about this. Sine square x plus cosine square x is equal to 1. You can solve for sine square x, you get 1 minus cosine square x. You can rewrite this. Sine theta becomes attached to the sine square theta, which becomes modified to 1 minus cosine square theta d theta. I've done nothing over here other than use this trigonometric Pythagorean identity. You can open this up. When you open this up, you get sine theta minus cosine square theta sine theta d theta. Nothing fancy over here at all. Separate everything into their separate integrals. You get sine theta d theta using the properties of integrals. You get cosine square theta sine theta d theta. Remember, we're talking about trigonometric substitution techniques. And think back to the early part of this video where I showed you the two rows of the types of questions. You can see the ones in those polynomial functions and the ones which are the trigonometric functions. There are two different classes of these substitution techniques. I'm showing you the lower row questions I was showing you earlier. like the types of, you can see, types of questions. But here we have something which is manageable. Look over here. This thing is easily solved and it's separate. This thing is easily solved using polynomial substitution. We'll keep looking at this on the side and we'll keep working on this for now. We'll look at right here and we'll do polynomial substitution. If u is equal to cosine theta, du is equal to minus sine theta d theta, and d theta is equal to du divided by sine theta, and you know you have the minus sign to worry about, and you work with this. I'm not doing anything with this until the very end. I'll keep writing it until I actually tackle it, because I know what this exactly is. U was cosine theta, so I have a u square, then I have a sine theta, and then I have a du over sine theta. I haven't forgotten about this minus sign. This minus sign would be attached to this du, which will affect this minus and make it a positive. These signs cancel out. I'm essentially left with this sine theta d theta plus u square du, which is all integratable easily in one step. Integration of sine theta, or the antiderivative, is minus cosine theta. U square becomes u cube over 3. Remember, 2 plus 1 divided by 2 plus 1, you get u cube over 3. But what was u? It was cosine. Cosine cube theta over 3 plus c. This right here represents the antiderivative of this, or the integral of this. And let's make this cube a little more better looking. So u square became u cube over 3, and u was cosine, so it became cosine cube over 3. And this right here is our final answer. We have a minus over here. Let's not lose sight of this minus. We can take the derivative of this antiderivative, end up back right over here to this. We can end up back right over here, and I want to show you that. This entire function over here. We'll do the derivative of this and separately. You see this cosine cube theta over 3? I'll write that out as 1 over 3, and I'm doing the derivative of cosine cube theta minus d over d theta cosine theta, which is this right here. I just wrote this first, then this second. But you're seeing it right over here. This right here is a composite. You have to use a chain rule. You'll do 1 over 3 d over du u cube, and then du over d theta cosine theta, because that's what your u is actually, minus the derivative of cosine theta is a minus sine theta. Now we have to look over here. 1 over 3 times u cube is 3u square. 3u square. But what was u? It was cosine, wasn't it, right? 3 cosine square theta. That's just 3u square. 3u square, that 1 over 3, and the derivative of cosine theta is a minus sine theta. Then I have a positive sine theta over here. These 3's cancel out. I basically have here a minus sine theta, which I'm writing first, attached to a cosine square theta, right? Cosine square theta, then a positive sine theta. What can I do from all of this? Remember, I'm trying to work this antiderivative back to this. I can isolate a sine theta. Let's isolate a sine theta. When I isolate a sine theta, I get here a minus cosine square theta plus 1. This thing is the same thing as saying 1 minus cosine square theta, which clues you back right over here. Because the sine square x is equal to 1 minus cosine square x. So 1 minus cosine square theta is equal to sine square theta. So you have sine theta multiplying by a sine square theta. And you can imagine that'll take us right to sine cube theta. And we'll be back to our original function right over there. So this is like yet another form of question you can see, except with the different functions, not only just sine. You could have seen the same question with any of those other functions, cosine, tangent, secant, whatever. So when it comes to trigonometric substitution integrals, I've shown you at the beginning of this video, based on those 2 rows of integrals, I showed you one row had the more of the reminiscent style of trigonometric functions, and there are a variety of substitution techniques or trigonometric identities that come into play with those. Then another row I was showing you was more of these forms, where you have polynomial style expressions, but within these polynomial style expressions there are trigonometric functions hidden or camouflaged. All you have to do is be able to recognize where and when, or what style of expressions are actually camouflaged And within these, those trigonometric integrals come out into the view, and you have to be able to make those recognitions. The recognitions are of three types. Look over here, in each of these cases you have a form of a composite, 4 minus x squared, and if you were to bring this up, you could use 4 minus x squared in parentheses to the power of minus 1. You could view this right here expression as 4 minus x squared to the power of minus 1 and dx. And you know both of these are in some form, these both expressions are to some form a composite. But what are you looking over here at? You're looking at some sort of numeral, and you're looking at a variable to the power of 2. A numeral and a variable to the power of 2. There are three types of these style of expressions you need to be aware of, and I'm going to show you all three, but this right here is style number 1. Style number 1 comes in this form, assuming you see these numbers over here, these you can call them as constant. If you want to say a represents a constant, then using this, and x here represents a variable, a trigonometric variable, assuming this in terms of our representation, we can come up with three scenario styles that you need to be aware of. One style is what you have right here before you. Something which looks like a square minus x square. Look at that. You have an a square minus x square, a square minus x square. Why is this a square? Because 4 has a perfect root and it's a 2. Just like this, it could have been a 25 for which the square root would be a 5. It could have been a 9 for which the root would be a 3. It could have been a 1 for which the root would be a 1. 16 for which the root would be a 4. Anyhow, all of these instances, these numbers represent an a, the letter a. When you have something which looks like in the style of a square minus x square, you start thinking of a certain trigonometric identity, because the whole purpose of these style of questions is for you to convert this into a trigonometric expression which will then be integrated. When you have something which looks like this, you want to be thinking of this type of identity. Sine square x plus cosine square x is equal to 1. And you solve this in terms of sine square x. Sine square x is equal to 1 minus cosine square x. That's exactly what we're looking at right here. 1 minus cosine square x. Except here, the 1 can be replaced by the letter a. So you have 1 square minus cosine square x. That's something what you're looking at right over here. A square minus cosine square x. So think of it in this form. When you see something like this, then you make two substitutions. Substitution 1 is this. X is equal to a sine theta, whatever this a might be, the square root of your perfect power, whatever that thing is, you do the square root for that and you get the a value right here. And then the derivative of this, of course, if x is your function or your substitution type, dx is the derivative of that, it would be a cosine theta d theta. Okay, and that's how you make your recognition. When you make these recognitions over here, and this right here is one of the form types you need to be aware of. If you see a square minus x square, you should be thinking this, you should be thinking that. Then how does this play out in terms of this specific example we have over here? These two and these two, I mean this one and this one kind of have the same form in terms of their composites, and they have the both a square minus x square form. So how does this play out in this role? It does. If you're seeing the 4 over here, you're thinking a is equal to 2. And then x over here is equal to 2 sine theta. I'm not going to solve these out. I'm just showing you the framework of how this plays into the future integration that we'll see. Then dx will be 2 cosine theta d theta. All of this has led to these items over here. Then you see these items over here, they'll somehow play into this expression or this expression. These are just hypothetical examples. Let's look over here. Then you look over here, and you'd see like this, you have a 4, which is really a 2 square, right? But we'll keep it a 4. And then you have x is equal to 2 sine theta, you plug that right in here, and it'll become 4 sine square theta. Because the square of 2 sine theta is 4 sine square theta. Then you have dx substitutes for everything over here. 2 cosine theta d theta. Now what happens? You have to work with this part over here. You could isolate technically 4, and you end up with 1 minus sine square theta. And then you still have 2 cosine theta d theta. But look over here, 1 minus sine square theta looks very much like one of these types of trigonometric identities, doesn't it? A Pythagorean identity. And you know 1 minus sine square theta can substitute very easily for a cosine square theta. And that's exactly what you're doing here. you're getting a 4 cosine squared theta within your radical. And then this can be simplified. The 4 cosine squared theta, when you do the root of it, you get 2 cosine theta. 2 cosine theta multiplies with this, you get 4. You'll get 4 cosine squared theta d theta, which now will go through its integration process. All you've done over here during this elaborate recognition process for something which looks like this, which is an a squared minus x squared type, all you've done over here is convert this polynomial style expression into something which is a trigonometric style expression, which will then go through the integration procedure to give you your final antiderivative. But you're seeing this play in front of you. That's exactly what I'm talking about. These style of questions are slightly more difficult. Why are they more difficult? Because they require you to recognize 3 types. This is just type number 1. There are 2 other types I have to show you. And I'm going to show you based on only on these specific examples I have right over here. I'll just modify the minus and the arrangement just to show you how the other 2 types will come about. So remember this as your 1 type. So now let's look over here. Here we have type 2. Look, the only thing I've changed over here are these signs. 4 plus x squared, 4 plus x squared, 4 plus x squared. What did I have before? I had 4 minus x squared. And these types are the same in terms of how you'll play them out. But I'm focusing here on this style over here for now. This will be handled exactly the same, because this right here is a composite due to the radical. This right here is a composite due to this parentheses and minus 1. Anyhow, what type is this? When you're looking at this, and a is a constant, x is your trigonometric variable, now you're looking at this form right here, a squared plus x squared. Previously we had a squared minus x squared, now we have a squared plus x squared. When you're thinking about this, or when you're seeing something in this form, you're thinking about this trigonometric identity. Tan square x plus 1 is equal to secant square x, and you can put a square over here, it doesn't matter, keep it the same across. And normally these types are those which are revolving around sine, cosine, tan and secant. You won't see much types involving cotangent and cosecant. But look over here. Here we have a numeral, and here we have a variable, numeral variable, because 1 square plus tan square x is the same thing as this writing the other way around. It doesn't matter. So when you're seeing something of this form, you're basically looking right here at this aspect only. So what does that tell you in terms of your substitutions you'll make? Well, they tell you this, that x will be a tan theta, then dx, the derivative of that will be a secant square theta d theta. With regards to these questions over here, but specifically this over here, how will this play out in terms of these substitutions? Well, a over here is going to be the root of 4, which is just 2. X will be 2 tan theta. Dx will be 2 secant square theta d theta. So now you're beginning to see how this is beginning to play out. We're converting something which looks like a polynomial expression, which is composited by some means, into something which will eventually become a trigonometric expression. Then that will go down the integral process. So looking at this and now looking at these substitutions, how will we address this? We're not going to solve it all, we're just talking about how we'll address it. We'll have 4 plus x squared, which will be 4 tan squared theta, and then the dx part right here will be replaced by this. I am out of space here, so I'm going to bring it down a little bit. 2 secant squared theta d theta. This part right over here still has to be isolated. You'll isolate something like this, like 4 into 1 plus tan squared theta. And 4 into 1 plus tan squared theta is looking just like this, which is going to be substituted here for a secant squared theta I wanted, right? And that 1 plus tan squared theta, which you isolate from these parts over here, will bring in a secant squared theta. You'll get a secant squared theta, and then you write the rest. 2 secant squared theta d theta. When you solve this part right here, the square root of 4 secant squared theta, which is why you're always dealing here with perfect roots to some form, perfect powers or perfect roots. The square root of this will become 2 secant theta. 2 secant theta will multiply with all of this, you'll get 4 secant cube theta d theta, and then this right here will go down the integration procedure. So this has now been transformed into this by means of this trigonometric substitution procedure, and you recognizing this type. So anytime you're seeing a square plus x square form, you're thinking of these substitutions over here because it's making you think of this. Remember, a square minus x square was bringing in the sine and the cosine. Well, a square plus x square is bringing you these set of substitutions, which will allow you to make these transformations to your original expression. There's only one more type we have to see, then we can actually go into actual examples. So this right here is the last style you have to be familiar with regards to these basic substitution techniques for trigonometric functions. But look, what have I changed over here? I've changed this, this, and this. Before I had 4 minus x squared and I had 4 plus x squared, but now I have x squared minus 4. So you can see the arrangement has been changed and we have a minus over here. This style is the hardest because this style right here is x squared minus a squared format. When you're looking at an x squared minus a squared type, you're thinking of this other trigonometric identity, similar to the one last before. Tan square x plus 1 is equal to secant square x, except here now you're looking at everything in terms of this. Secant square x minus 1 right here. Secant square x minus 1. Secant square x minus 1 square. A could have been here, any perfect square over here. When you're looking at something of this form, what are the substitutions you're making? Well, you know a is going to be what are the root of the number you're looking at, but your x will be here a secant theta. Therefore dx right here will be a secant theta tan theta d theta. This is why I'm saying this is the hardest one, because you bring in this slightly more difficult expression to deal with. This is slightly more difficult to integrate. This is slightly more difficult to integrate. Anyhow, these are the set of substitutions you'll make. With regards to this specific question, because the theme has been here just looking at this, what will our a value be? A value here is a 2, right? What will our x value be? X will be 2 secant theta. What will dx be? It will be 2 secant theta tan theta d theta. Now, how will we look at all of this with regards to this? Well, it shouldn't be too hard, but let's show you. We're not going to solve it out, we're just laying the framework here. Within the square root, you're going to have x squared minus 4. Here's my x. 2 secant theta will be 4 secant squared theta minus 4. And then dx will be all of this. 2 secant theta tan theta d theta. You have to simplify this. And how does the simplification occur? It occurs by means of isolation and bringing in a trigonometric identity for substitution. When you do this, you get 4 into secant square theta minus 1. If you were to open this up, you'll end up back here. But secant square theta minus 1 is equal to what? Secant square theta or secant square x minus 1 is always equal to tan square x, right? Or tan square theta. So when you do this little maneuver over here, it enables you to bring tan square theta over here, or tan square x based on your variable type. Tan square theta, then you have 2 secant theta tan theta d theta. When you do this, the square root of 4 tan square theta, you get 2 tan theta. 2 tan theta multiplies with all of this, and you end up converting everything over here to this. You have 2 tan theta multiplying with all of this, you'll get 4 secant theta tan square theta d theta. So now this is the expression, the trigonometric expression, which will go into the integration process. You've converted something which looks like this into something which looks like this. And I've shown you likewise everything, these 3 types, this was type number 3, all converted eventually into some trigonometric expression which will go into the integration procedure. So now all that remains is to put everything we've learned in terms of these frameworks for the trigonometric substitution techniques into practice. But before I do that, I want to very quickly summarize these 3 types, because I know these 3 types can be a little overwhelming at first. To alleviate that overwhelming feeling we might have, let's do a very quick review. Assuming that a represents your constant and x represents your variable, for that original integral expression that eerily looks close to a polynomial, we want to somehow be able to convert it into trigonometric integrand, which can go down the integral procedure. These are the types you should be familiar with. Anything which looks like this, a square minus x square. Think about this. Your substitutions will be this. If x is equal to a sine theta, then the derivative of that which will be placed will be a cosine theta d theta. And something of this form, a square minus x square, you can imagine would be some question looking like this. Let's just put any number over here. We can even let's put 16 minus x square dx. A square minus x square. Something of this form. Another type we know we have is this a square plus x square, but you can also see it as x square plus a square because order does not matter when it comes to adding. When you're looking at something question which looks like this is what you should be thinking. X in terms of substitution is a tan theta. You know the a is very easily obtained. You can do the square root of your numerical value. The dx here will be a secant squared theta d theta. A question which might look something like this. Example over here would be, let's say 4 plus x squared to the power of 3 over 2 dx. And these dx's and x's here can be replaced by thetas, d thetas. Another type you might see is this, x squared minus a squared. Perhaps the hardest in my opinion. Anytime you're seeing something of this framework, you're thinking this, x is equal to a secant theta, dx is equal to a secant theta tan theta d theta. An example of a question which might look something like this, you can come up with any combination, but you might be looking at a question which is x squared minus 25. A question of this form, you're thinking of this. You can even have something like this. For a similar type right over here, you could have x squared minus 1 to the power of, let's say 3 over 2 dx. These are these type of forms, these types. So here's your type 1, be familiar with that. Type 2, order does not matter over there. And type 3. So I've presented you the 3 types. I want to present an example of each of these, starting with a squared minus x squared. Look over here, a squared minus x squared. And this is the type I want to talk about first. Then I'll show you an example of this type and an example of this type. When you're seeing an a squared minus x squared, what are the things you're thinking about in your head? You take this number, you square root it, a is equal to 4. Another thing you're thinking about is 4 sine theta. Dx is the derivative of this, which is 4 cosine theta d theta. These are all things I talked about right before these examples I'm about to present you. The methodology behind all of this, where you look at a polynomial expression which looks something like this and you convert it into a trigonometric expression which you then integrate, and these all represent various areas under a curve. Anyhow, you modify that initial question with these substitutions. Dx is 4 cosine theta d theta. This dx is that right over here, substituting for that, over 16 square root minus x squared. This x squared right over here is going to substitute for right over there. 4 sine theta squared is a 16 sine squared theta. Look right at this area. You have a 16 minus 16 sine squared theta. You can isolate 16 and you can get 1 minus sine squared theta. And based on the trigonometric identity, this is the same thing as 16 cosine squared theta. Because sine squared theta plus cosine squared theta equals 1. If you solve for cosine theta, you get 1 minus sine squared theta. So all of this substitutes for this. So in all of this radical area, right, we can substitute this 16 cosine squared theta, which are all perfect squares. You can now do a perfect square root. You do a perfect root of this and you compute it with regards to your numerator. What's the square root of this? It's a 4 cosine theta. All of this cancels out. What do you end up getting? Integral of d theta, which you know easily to be theta plus c. This right here is actually your answer, but this is not a very good answer, because if you took the derivative of this, you're not really going to end up back at an expression which looks like this. But if you write your expression in terms of theta right here, this theta over here, you can come up with a better answer. Look, if x is equal to 4 sine theta, then theta is equal to, you take everything on the other side, arc sine, you take sine on the other side, it becomes inverse sine or arc sine, same thing, x over 4. Now write your answer with regards to this. Your final answer is really arc sine x over 4 plus c, or you can say sine minus 1 x over 4 plus c. You can do the derivative of this antiderivative and you'll end up back over there. And you can see that, and I'll show you partly that, not entirely but partly. Look, you'll do the derivative of this. It's a composite. D over du sine minus 1 u du over dx x over 4. If u is equal to x over 4, f of u is equal to inverse sine u, and that's how I'm getting all of this. You know the integral of this is going to lead you to this 1 over 1 minus u square. The derivative of this is going to lead you to that. The derivative of this is going to be 1 over 4 times 1 over 4. When you resubstitute back what u was, x over 4, what are you going to get? You come over here, you get this 1 over 4 at the very beginning. Let's put that over there. Then you have 1 over 1 minus x squared over 16. How am I getting x squared over 16? Because u was x over 4, u squared is x squared over 16. You'll manipulate all of this algebraically. This entire expression is here under the radical 1 over 1 minus x squared over 16. You'll do all of that manipulation, algebraic, solving, simplifying, and then it'll bring you right back to here. Always present your answers not in this form right over here, but always in this form where you're actually representing what your theta was. If you present your answer like this, it's vague because you don't know what theta really was. When you present your answer in this form, it's not vague at all and it's better answer. Let's look at this question here. Integral of dx divided by x squared plus 25. You know you have something which looks like this. A squared plus x squared or x squared plus a squared. When you see something of that form, you come up with a few items. A over here is equal to 5 because square root of 25 is a 5. X is equal to 5 tan theta. Dx is equal to 5 secant square theta d theta. And that's what you're going to substitute for this trigonometric substitution procedure. The dx over here is 5 secant square theta d theta. Here you have x square, which is this 5 tan theta becomes x square, becomes whole square. You get 25 tan square theta plus 25. You can isolate from here. You can isolate 25 and you get tan square theta plus 1. You know this right here is equal to secant square theta. So all of this over here generates this item over here. So let's rewrite it here again with the condensed format here. You'll have 5 secant square theta d theta in the numerator. Here you get 25 secant square theta. What can you cancel out over here? These can cancel out. What you end up with is basically d theta over 5. When you do the antiderivative of that, you get theta over 5 plus c. Now technically you can do the antiderivative of this and somehow work it back over here, but you'll have to do some substitutions, which is why it's always better to present your answer using this in terms of theta. If x is equal to 5 tan theta, theta is equal to arc tan. You take tan on the other side, you become inverse tan of x over 5, and you can use that as your answer in place of theta. You get arc tan x over 5 divided by 5 plus c. This becomes your antiderivative. Now you can do the derivative of this antiderivative and you can end up back over here. You know you can also rewrite your answer like this. Bring the 1 over 5 on the side and then you can do tan minus 1 x over 5 plus c. This type of answer or this type of answer, which one is better? This one right here is better. This one is not as good because here you're leaving some ambiguity, like what was theta initially represented by. So you always have to come back over here. This answer is better because here you don't have any ambiguity what you're talking about. You presented your answer in a better form. So let's look at this question over here. The integral of dx divided by x squared root x squared minus 25. You're looking over here. It looks something like this, x squared minus a squared. So this is like the third type. And you know in all of these questions you're using these type of methodologies and their substitutions to convert something like this into a trigonometric expression. Then you can use identities and your various techniques, substitution procedures to actually get to the antiderivative. What are the substitutions that will come in place? A is equal to 5. X, when you see something of this, you're thinking 5 secant theta, then dx, the derivative of that is 5 secant theta tan theta d theta. And I told you this form is usually harder because you end up with expressions there which are slightly more difficult to deal with. Anyhow, make your substitutions. The dx is exactly what you're seeing over here, 5 secant theta tan theta d theta. X square is basically this square right here. 5 secant theta square of that is 25 secant square theta. In the parentheses you'll have x square again, 25 secant square theta minus 25. Just looking at this part right here, you're isolating 25 and you're getting secant square theta minus 1. And here secant square theta minus 1 is equal to tan square theta using the trigonometric identity. So over here you'll get 25 tan square theta. All of this will simplify into 25 tan square theta, which will be perfect squares. Now you can simplify this. You can't do much right here with the numerator yet, but you will soon. Here you have a 25 secant square theta. Here you have root of 25 tan square theta, which is 5 tan theta. This tan theta, this tan theta, this 5 cancels out. This secant theta cancels out with this 2 over here, exponent 2. What you end up with eventually is basically right over here. You'll have d theta on the top and you'll have 25 secant theta. You can bring out the 25 as 1 over 25 and you'll have this d theta over secant theta. You know reciprocal of secant theta is what? Cosine theta, right? You have this cosine theta d theta playing out. This right here is equivalent to that. Cosine theta is reciprocal of that is secant theta. Reciprocal of this is back to that. Antiderivative of this, what's your final answer? Is 1 over 25. Antiderivative of that is sine theta plus c. But I told you when you're writing your answers in terms of thetas, it's not as good. What was theta originally equal to? Look back over here. Theta is equal to, let's write over here, what is theta equal to? If you solve for theta in this expression, you take everything on the other side. Theta is equal to arc secant. You're taking secant on the other side, arc secant x over 5. Use this in terms of theta right over here. What's your final answer? Is 1 over 25 times sine of arc secant x over 5 plus c, and that right there is a better answer. What exactly does this expression right over here actually mean? You have to think back to something we talked about a long time ago in the precalculus videos. You have to think back to a diagram that you would make. Let's make a quick rough diagram. Right triangle. Here's my theta. Arc secant x over 5 means secant. In terms of secant, you're looking at x over 5. What sine of this? You have to find the third. Think back to that video I showed you in trigonometry a long time ago in precalculus videos. How do you find this missing side? What is it going to be? It's going to be x squared minus 25. X squared minus 25. A squared plus b squared is equal to c squared. This will be that. What sine of all of that? Sine in terms of the theta will be this. Square root of x squared minus 25 over x. That's what you're really looking at. This. Anyhow, this right here is just a side note, but this right here is your final answer, a better answer than this right over here. We have presented all the core fundamentals with regards to this video, the trigonometric substitution techniques from a general perspective, and I've talked about these type of questions you can see, and then these type of questions, a square minus x square, a square plus x square, or x square minus a square form, and I've shown you kind of the convention of these in terms of their values. When we get the antiderivatives of this, hypothetically it's fine if your final answer is in the form something x theta plus c. Whatever this x might be, some sort of function, and for this if your answer is in the form x theta plus c, then you want to do over here the substitution for a better answer for these type of questions, substitution of the theta value, so you can bring in the inverse trigonometric function so that your answer would then convert into this form. It could be, hypothetically speaking, let's just say hypothetically, sine minus 1 and some function over here plus c. When you're having a question of this type, try to get your answer here in terms of the substitution of the theta. Take it one step further. When you have a question of this type, you can present an answer in this form and you will be fine. So these are the types of answers you should be aiming for over here for these specific type of questions. So now for the remainder of this video, we're just going to go through a barrage of examples, practice examples. So we can be looking at types of this form and we can be looking at types of that form. And remember, these trigonometric substitution questions can become quite complex. It just basically depends on your level of formality. Do you want to keep things to a general perspective, something more practical? And it also depends on how deeply you want to delve into this. Of course, as a presenter, I'm not going to provide questions that are overwhelmingly complex, because then I'll never be able to fit them on this board. It would become a haphazard style presentation then. I'll be presenting those type of questions which I can easily fit on this size board, and it can be practical, of practical value and significance. So when you see these type of questions, you're kind of lucky, because they're basically trigonometric identity or polynomial substitution questions which are disguised in the form of trigonometric functions. So you can handle them easily. You look at the more complex and you make your substitution by that. U is equal to sine theta, du is equal to cosine theta, d theta, and then d theta is equal to du over cosine theta, and you proceed with that. You'll have a u cube, and then you'll have a cosine theta, and then du over cosine theta. You can cancel these out. These type of questions are not hard. You're essentially just left with u cubed du, which you know is u4 over 4 plus c, but you have to resubstitute back the u. U was this sine theta. You get sine to the 4th theta over 4 plus c. And this right here represents a good final answer. You can even write this as this, though the way I'm showing you is the better way, sine to the 4th over 4 plus c. This right here is perhaps the better way of showing it. So this right here would be a good answer for this type of question. Remember, these type of questions are easy. You can take this right here, this entire value, and you would do the derivative of that antiderivative, and you'll end up back to exactly where you were right here. You might have to involve some sort of trigonometric identity to bring it to this form, but this can easily go back to that form. Let's look at this question over here. Cosine cubed theta d theta, a definite integral question from a lower limit theta equals 0 to an upper limit pi over 2. You're technically basically calculating the area below the curve within that defined interval we have, 0 to 90 degrees. How do you proceed with this type of question? And I showed you something like this, except it was sine cubed theta at the very beginning of this video. Separate it into these parts, cosine squared theta d theta, and you have pi over 2 and 0. Use a trigonometric identity for right over here. Sine squared theta plus cosine squared theta equals 1. Cosine squared theta equals 1 minus sine squared theta, and use it in that form. Pi over 2 is 0. Cosine theta, and then here you have 1 minus sine squared theta d theta. Open up the parentheses. Pi over 2 is 0. Cosine theta minus sine squared theta cosine theta d theta. Separate using the properties of integrals across the minus sign. Pi over 2 0 cosine theta d theta minus pi over 2 0 sine squared theta cosine theta d theta. This can be easily handled. It's one step away from completion. This right here is almost a few steps away from completion. Polynomial substitution technique plays over here. And then when you do polynomial substitution, you have to alter these intervals, as you know. If u is equal to sine theta, du is equal to cosine theta d theta, and then d theta is equal to du over cosine theta. You've altered these intervals with this substitution. Therefore, if this was theta 1, this is theta 2, now you have a u1 and a u2. u1 and a u2. And you know these values are put right here. Sine of 0 is a 0, that's your u1. Sine of 90, we're looking at right here for our substitution. Sine of 90 is a 1, that's our u2. Come back over here. We'll keep writing everything out until it's completion time. Pi over 2 0 cosine theta d theta minus 1 and 0, my new intervals. These were theta 1, theta 2, this is u1, u2. We'll have a u square cosine theta du over cosine theta. These will cancel out. What do we end up having? Pi over 2 0 cosine theta d theta minus 1 0 u squared du. Integration of this will lead you to sine theta over a limit of pi over 2 and a 0. The integral of this will give you minus u cube over 3 over the values 1 and 0, and you have to solve them out. This solving out procedure is not hard. You'll do sine 90 minus sine 0, which is just a 1. You'll get a 1 right over here, because sine 90 is a 1 minus sine 0 is a 0, you'll get a 1. This part right here alone is generating you the 1. Here you'll do 1 cube over 3 minus 0 cube over 3. You'll get a 1 over 3 from this part right over here. 1 minus 1 over 3 is a 2 over 3. And that right here is our final answer. That final answer of 2 over 3 represents the area of this curve within the interval. 2 over 3. That's our final answer. Let's look at this question. It's another definite integral question. Lower limit x equals 0 to an upper limit x equals 3. We're looking at a function over here which represents a calculation of a certain area below the curve. And you know, when you're looking at these type of questions, you're looking at a different type of trigonometric substitution question, the type of this form, x squared plus a square. When you see of these forms, x squared plus a square, or x squared minus a square, or a squared minus x squared, you're looking at a certain number of things. A over here equals 3 square root of 9. X over here is equal to 3 tan theta. Dx is equal to 3 secant square theta d theta. All our substitutions are done for the initial part of this question. Now, these are the original intervals. This substitution leads you to a new bunch of intervals, the theta 1 and the theta 2, which you have to calculate. How do you calculate these? Well, you look at this equation and it equals these x values. See these x values. Let's do them right over here, then I'll erase it. 3 tan theta is equal to x1, which is equal to 0. Tan theta is equal to 0 over 3, which is equal to 0. Theta is equal to inverse tan of 0, which is 0 degrees. So theta 1 is equal to 0. Now, let's do this. 3 tan theta is equal to x2, which is equal to 3. Tan theta is equal to 3 over 3, which is 1. Theta is equal to inverse tan of 1, which is pi over 4. Pi over 4. We can make this in radians, 0 and pi over 4. Those are our new intervals. So keep all of this in mind as to how these things play out. We have everything set over here now. Now we do our substitution over our new interval. Pi over 4 and 0 dx 3 secant square theta d theta x square 3 tan theta square is 9 tan square theta plus 9. Look at this part. 9 into tan square theta plus 1, 9 into secant square theta, because a certain trigonometric identity gives you that. And that is what you plug in over here. Pi over 4, 0, you have 3 secant square theta d theta over the square root of 9 secant square theta. Perfect squares over here, perfect roots can be obtained. You have pi over 4, 0, 3 secant square theta d theta over 3 secant theta. Cancel the 3's, cancel the secant theta, and you will eliminate that power. What you end up with is this: pi over 4 upper interval and 0 lower interval, secant theta only. Secant theta d theta, and you remember the integral of this is what? Natural log secant theta plus tan theta in absolute value parentheses over the interval pi over 4 and 0. So how are you actually going to solve this? It's not hard by any means. You're going to do a natural log of secant 45 plus tan 45 minus natural log secant of 0 plus tan 0. And you can think about your trigonometric ratio triangles over here. Let's do that. Trigonometric ratios. When you're looking at a 45-degree triangle, you have a 1, 1 and a root 2. And that gives you your values you need. So when we're doing the first part using the upper limit, this is what we'll get. We'll get natural log of secant of 45, which is a root 2, plus tan of theta, 45 is just a 1, minus natural log secant of a 0 is just a 1, because cosine 0 is a 1, therefore secant of 0 it must be a 1, reciprocal of 1 is a 1, plus tan of 0 is a 0. All of this will zero out because natural log of 1 is a 0. You're essentially left with just this term over here. natural log root 2 plus 1. You can get a calculator value for this natural log root 2 plus 1, which will represent the area under the curve over these intervals right here, 0 to 3, 0.8813. That right there is the numerical answer for this right over here. 0.8813, the area under the curve. And this question is done, and we would be right. I'd have to apologize for the lighting issues in my videos lately, because we're in Minnesota here right now, and the lighting is bad nowadays because of the early dark hours. So that's why you'll see various colors arise in the board during my presentations lately. It's just the effect of the winter and the low ambient light. Anytime you see a question like this, especially for sine square theta or x, or cosine square theta or x, you should be handling this question in terms of a power reducing formula. Do not separate your question into this sine theta, d theta, and then try to do this integrating by parts. You're going to end up complicating the question if you make it this into that form. Just use your power reducing identity and treat it that way by means of a basic integral question. And this is what I mean. You know sine square theta, and I've shown you this in the verifying trigonometric identities video near the end, where I showed you how this can be viewed in the same manner as cosine 2 theta over 2. I've shown you the derivation of this, and I've also shown you the derivation of this. This was 1 plus cosine 2 theta over 2. But for this question, you're going to be utilizing this part right over here. So this is what you have to substitute for this, and your question fundamentally changes. And this is called a power reducing because you're reducing the power. Here you're dealing with an exponent of 2, here you're dealing with an exponent of 1. It's easier. This should be separated into separate integral forms over this minus sign. You get a 1 over 2 d theta minus 1 over 2 cosine 2 theta d theta. You can see how I've separated this. You had a 1 over 2 over here, then you had a cosine 2 theta over 2. I just brought the 1 over 2's outside the integral sign, and we've done this. This part right here is very easy. This part right here is a composite, so you do a polynomial substitution for this part. U is equal to 2 theta, du is equal to 2 d theta, and d theta is equal to du over 2. And you'll do it here, and you'll do this separately. This right here is one step away from completion. I won't complete it yet until I'm ready to complete everything. Over here I'll get cosine u du over 2. This over 2 can be brought out here, and we can increase this to a 4, 1 over 4. Now let's finish the integration of both of these. These are easy. 1 over 2 d theta is basically just theta over 2. Theta over 2. This right here will be sine u over 4. Sine u over 4, but u was 2 theta plus c. So this right here would be your final answer, and you can roll with this right over here. You could do the derivative of this antiderivative, and you can end back right exactly where you were. For this question here, cosine to the power of 4 theta, sine theta, d theta, another definite integral question from 0 to 60 degrees. It's a trigonometric substitution technique disguised in a polynomial substitution question. That's all what it is. U is equal to cosine theta, du is equal to minus sine theta d theta, and then d theta is equal to minus du over sine theta. Because we're dealing here with a definite integral, we have to get a new bunch of values there for u1 and u2. u1 and u2. What is u1 is going to be cosine of 0. Cosine of 0 is a 1. u2 will be cosine of 60, which is a 0.5. Because 60 degrees cosine is a half. So you end up rewriting your question as this. You end up having a lower limit of a larger number and an upper limit of a smaller number, which is fine, we'll worry about that. Cosine was substituted for u, so it was a u4 sine theta d theta over sine theta, and this should be here du. That was our substitution, du. And you know we have a minus sign, we can't forget about that. You can flip the interval around by using the properties of integrals. If you bring another minus sign, it allows you to flip the interval. You can do minus, minus, the original minus from right here, and you can add another minus to flip the interval around, 1 and 0.5. And then you have a u4 and a du. So don't forget about this minus technique. If you have a reverse interval, you can add another minus sign and flip the interval around. I've shown you that in my properties of integral videos. So don't forget about this technique over here. These two minuses make everything positive, they nullify each other, and you end up looking at this u to the 4 du, which you know integrates to u to the 5 over 1 and a 0.5. And you know, to do this integration over here is not hard. You'll be looking at 1 to the power of 5 over 5 minus 0.5 to the power of 5 over 5, which on your calculator you can easily do. And you can come up with this answer, 0.19375. This will represent the area under the curve from this interval to this interval, and this right here is our curve. And let's look at this question here. Tan cubed theta d theta, integrating this definite integral from 0 to 45 degrees. Look at your question in this form. Split it up as tan theta and then tan square theta d theta, 0 to 45. I've just separated the cube into a single order and a double order function, and you can proceed with it that way. And think of a trigonometric identity which involves this. You know, tan squared theta is equal to secant squared theta minus 1 for tan squared theta. You can do that substitution over here. Right here, the trigonometric identity, the Pythagorean identity, that's what we're focusing on here. And then separate everything over here. You'll do tan theta secant squared theta d theta minus tan theta d theta. And you'll have pi over 4 over here, pi over 4 here, 0 here, and 0 here. We haven't done anything out of the ordinary at all so far. The hardest part so far was this, creating this identity substitution. That's all what it was. This right here is very easily done. This has to require a little bit of a work over here. The best way to handle this is a polynomial substitution technique. And you have to somehow eliminate the secant squared theta, and you can do that by this. If u is equal to tan theta, then du is equal to secant squared theta d theta, and then d theta is equal to du over secant squared theta. And you know, then you have to do a new set of intervals there, u1 and u2. u1 will be tan of 0, which is 0. u2 will be tan of 45 degrees, which is a 1. So you basically converted this into a 0 and a 1. U value of 0, u value of 1. And you've gotten here a u secant squared theta, then du over secant squared theta. These cancel out, and you still have this other integral over here you still have to worry about, but it's easy. Now you basically have u du. This will integrate into u square over 2, and you still have this 1 and 0. And then you have tan theta, which will integrate into natural log secant theta over the interval 45 degrees and 0. You're basically looking over here in this thing, right over here, 1 square over 2 minus 0 square over 2. And then you're looking over here, natural log secant of 45 degrees minus natural log secant of 0 degrees. You have to compute all of this. From this, you're just going to get a 1 over 2. That's easy. From this, what are you going to get? 45 degrees. Think of a trigonometric ratio. When you have a 45 degree, you have a 1 root 2. Natural log of a 45 is giving you a natural log of a root 2. Natural log of secant 0 is 1. Secant of 0 degrees is 1, so you're looking at a natural log of 1, which you know zeroes out. You're basically just looking here at natural log root 2. So you're doing 1 over 2 minus natural log root 2. Let's look at this question. The integral of sine to the power of 4 theta d theta. You want to look at this question like this. Sine squared theta d theta. And that's how it's going to get you through. And then you're thinking about the power reducing formulas, where you know each sine squared theta is equal to 1 minus cosine 2 theta over 2, and that's how you have to proceed. If you think about each of these as equaling to a power reducing formula, you're looking at this. 1 minus cosine 2 theta over 2 multiplied by 1 minus cosine 2 theta over 2 d theta. And then you have to multiply everything. When you multiply everything, you can see this 2 and the 2 will multiply to give you a 4, and you can bring the 1 over 4 out. 1 over 4 out. That's this 1 over 2 times 1 over 2, you're getting that 1 over 4. Now you have to do FOIL, first out, inner last, for everything here on the numerator. When you do that, you'll get 1 minus 2 cosine 2 theta plus cosine square 2 theta d theta. That's what you get when you multiply all of this out. separate everything into their own integral signs. This with this, this with that, that with that, and you'll get this 1 over 4 d theta minus, you see this 2 will multiply with this 1 over 4, you'll get 2 over 4. When you do that 2 over 4, you can simplify to 1 over 2. I'm multiplying 1 over 4 with this, 1 over 4 with this, 1 over 4 with that. And I'm writing each with their own integral signs. When this 1 over 4 multiplies with this 2, you get a minus 1 over 2. See, 1 over 4 times minus 2 is a minus 1 over 2. You'll get a cosine 2 theta d theta. 1 over 4 with this. 1 over 4 cosine square 2 theta d theta. Now over here you have a composite. If u is equal to 2 theta, if u is equal to 2 theta, du is equal to 2 d theta, and d theta is equal to du over 2. I'm looking at this one right over here. I'll write everything else I see it. 1 over 4 d theta. This 1 over 2 with this 1 over 2, you'll get a 1 over 4. And here you get cosine u du. You can see this, all of this right here, with the effect of this brings you that. Now look, where I have another aspect over here which can go through its own, it can go through its own power reducing formula. Cosine square, the cosine square theta is equal to 1 plus cosine 2 theta over 2, but this is cosine square 2 theta, and that would make this right over here open up into this 1 over 4. You'll get 1 plus cosine 4 theta, because you have a 2 over here. In this formula presence over here, you get a 4 theta over here, d theta over 2. So this question can get a little messy. Let's erase some of these items over here and make space. All of this right over here, you have 1 over 4, 1 plus cosine 4 theta over 2 d theta. We can separate this out into its own individual ones. This 1 over 4 with this 1 over 2 will give you 1 over 8 d theta, and then you get 1 over 4 times 1 over 2, you'll get 1 over 8 cosine 4 theta d theta. I'm just doing the simplification of this part only. So for this over here, we can do a substitution. If v is equal to 4 theta, then dv is equal to 4 d theta, and d theta is equal to dv over 4. So all of this modifies to all of this right here. 1 over 8 d theta plus 1 over 8 times cosine v dv over 4. This over 4 can come out with this over 8, and you get 1 over 32. So let's bring all of this into play right over here by making space. This question gets a little messy because it's a little long. So I've shown you this over here transformed into what was originally here, which is right over here. Right over here, and this transformed into all of that, which transforms into all of this. I'm going to write this in simplified form. 1 over 8 integral d theta plus 1 over 8 times 1 over 4 is 1 over 32 integral cosine v dv. So you've seen all of that come into play. We've essentially now gotten this as our line of expression. Just remember the original substitution. U was equal to 2 theta and v was equal to 4 theta. Now let's integrate all of this, and this is indefinite integral. 1 over 4 d theta will become theta over 4 minus integral of cosine u is a sine u. Sine u was a 2 theta over 4. 1 over 8 d theta is a theta over 8. 1 over 32 integral of cosine v will be a sine v over 32 plus sine v, which is a 4 theta over 32 plus c. But we're not done. These two are like terms. Theta over 4 plus theta over 8 gives you something. It gives you 3 theta over 8. If you do this right there, you get 3 theta over 8. So let's do 3 theta over 8 minus sine 2 theta over 4 plus sine 4 theta over 32. And this right here is your final answer. Messy, but it's right. Let's look at this question. Definite integral 0 to 1 dx over x squared plus 1 whole square. We're seeing something of this form, x squared plus a squared, which is the same thing as a squared plus x squared. And you know these are the substitution items you're thinking about. A is equal to 1, x is equal to 1 tan theta. The 1 is meaningless here. Dx is equal to secant squared theta d theta, and you make your substitutions for just that part right over here. We still have to worry about this new interval values How do you get your interval values? You look here at this expression here. Tan theta is equal to x1, which is equal to 0, and then the other expression is tan theta is equal to x2, x1 and x2, which is equal to 1. Here theta 1 is equal to 0 degrees, theta 2, you're doing inverse tan of 0, inverse tan of 1, which is pi over 4 for your theta 2. And we have everything we need now. Look over here. 0 to pi over 4. Substitute dx, secant square theta d theta over tan theta square, which is tan square theta plus 1 whole square. What do we get over here? Pi over 4 and 0. This right here is equal to secant square theta. Now you know that. Secant square theta square is a secant to the 4th theta. Secant square theta divided by secant to the 4 theta d theta. You can simplify all of this. These things cancel out such that you end up with this in the denominator. Pi over 4, 0, 1 over secant square theta d theta. Right? Because this square over here cancelled out with that 4 and made it into a square. But this thing can entirely be written by its reciprocal form, which is, I'm going to be showing you, cosine square theta d theta. And here you're going to use a power reducing formula. Cosine square theta is equal to, and I'll show you right over here, it's equal to 1 plus cosine 2 theta over 2 d theta, and you have a pi over 4 and a 0. Now we have to try to finish this in the remaining question. Space we have, and we're going to separate this out. We have over here pi over 4, 0, 1 over 2 d theta. I'm separating everything around this positive sign right over here, positive sign. Cosine 2 theta over 2 plus 1 over 2 cosine 2 theta over 2 d theta, pi over 4 and 0. Now let's do some substitutions. U is equal to 2 theta, du is equal to 2 d theta, and d theta is equal to du over 2. We're looking at this right over here. It will change our values also now, these interval values. You're going to multiply everything by this 2 theta. Here's theta 1, here's theta 2. u1 becomes 2 times 0, which is a 0. u2 becomes 2 times pi over 4, which is pi over 2. So when you do all of this, you reconvert all of this into what I'm going to show you right over here. You convert everything into this. Cosine u du over 2 from 0 to pi over 2, but this over 2 and this over 2 will convert this into an over 4, and we can eliminate this denominator right over here. Now you basically just have to integrate everything from right here up to right over here. So let's do that, and let's erase this so we can take everything to completion. You have everything before you, you can rewind it and look back at it. Integral of this d theta 1 over 2 is just theta over 2. Theta over 2 over the pi over 4 and 0 interval. This one right over here will be cosine u, will be sine u over 4 over the pi over 2 and 0 interval. You're basically doing pi over 4 divided by 2 minus 0 divided by 2, which you will just get from that first part, just pi over 8. Why am I getting pi over 8? Because there's a pi over 4 divided by 2 is a pi over 8. All of this will yield to pi over 8 because a 0 over 2 is meaningless. From here, what will you get? Sine of 90 divided by 4 minus sine of 0 divided by 4. Remember, it's always the upper limit placed into your this value, minus from that the lower limit placed into that. Here you're getting a 1 over 4. This right here can represent a good final answer. Or you can convert this into a decimal. If you were to convert this into decimal, you do pi divided by 8 plus 0.25 and you get 0.6426. 0.6426 or 0.643 for being the area in the curve from this interval to that upper limit interval, lower limit to the upper limit. And yeah, pi over 8 plus 1 over 4, 0.643 are both equally good answers. So this video on trigonometric substitution techniques is just a general overview of the substitution procedures with regards to the trigonometric substitution technique. I want to present two more examples and that'll be it for this video. Let's look over here. We have a square minus x square form. A square minus x square forms. We know a is equal to 3 and we're looking at something of this nature. X is equal to 3 sine theta and dx is equal to 3 cosine theta d theta. Alright, of this form. From here we get these substitutions. Indefinite integral, so that's good. We have 3 cosine theta d theta in the numerator, and here we get 9 minus 9 sine squared theta to the power of 3 over 2. You know all of this right here is going to give you something. You can isolate 9, you'll get 1 minus sine squared theta. 1 minus sine squared theta is equal to cosine squared theta. So here you get 9 cosine squared theta to the power of 3 over 2. What's 9 to the power of 3 over 2? You can figure that out. It's not hard by any means. You can do your calculator 9 to the power of 1.5, or think of this as 3 square. The over 2 and that square will cancel out. You'll end up having 3 cubed, which is 27. You can see that on the calculator. This is what I'm doing. I'm converting 9 into 3 square and I'm multiplying by 3 over 2. These cancel out. I get 3 to the power of 3. Same logic can be applied to the cosine square aspect, and that will give you cosine cube. You get 27 cosine cube. Remember, some of these things you can always do on your own. Cancel things out. When you cancel things out, what do you get? You get d theta on the top. You get 9 cosine squared theta. You can get everything pushed up. Keep the 1 over 9 out. I've taken the 1 over 9 out. Cosine square reciprocal is equal to secant squared theta d theta. So when you're up over here at 1 over 9 secant squared theta, you know there's something. If you were to do something like this, if you have something which looks like secant squared theta and it gives you something over here, and you take the derivative of this antiderivative, you end up back, and you know what this can be. It's tan theta, and I've shown you this in one of the earlier integral videos. So this right here, 1 over 9 secant squared theta d theta, translates into 1 over 9 tan theta plus c. But I don't like the appearance of this final answer because I want everything here to be with regards to this. You see this x is equal to 3 sine theta. If x is equal to 3 sine theta, theta is equal to inverse sine or arc sine x over 3. And I can write this in this form. I get 1 over 9 tan arc sine x over 3 plus c. But what does this mean? Tan of arc sine x over 3 plus c. How can we reconcile that? Well, we can. If you draw one of these types of triangles and make a 90-degree, and you have this, you're looking at arc sine x over 3. You know sine is always opposite over hypotenuse x over 3. To get this, you're doing a squared plus b squared is equal to c squared. You solve for this, you get 9 minus x squared. So what is all of this in terms of this triangle we've drawn? We're looking at 1 over 9 tan of this. We're looking at the tan. It's really x. Tan of this triangle is x over this, opposite over adjacent, over 9 minus x squared. That's what we're looking at. If you want to rewrite this in a more condensed form, you can x over 9 root 9 minus x squared plus c, and you can look at your answer in this form as well too. If you were to take the derivative of this antiderivative, you will surely end up over here, and that's something you can try on your own, but you will. Both of these answers are good. This answer over here is fine, but it's a weak answer. This answer right here is good. This answer is even better, because you're representing here with regards to the triangle. Each of these answers builds upon each other, and this answer is the most meaningful. So let's look at this. Integral of x cubed divided by square root of 4 minus x squared, an indefinite integral. You're looking at this form over here, a squared minus x squared, and you know a is equal to 2, x is equal to 2 sine theta, dx is equal to 2 cosine theta d theta. Substitute that right over there. X cubed will become 8 sine cubed theta. I took this 2 sine theta and I cubed it. Square root of 4 minus x squared would be 4 minus 4 sine squared theta. Dx is all of this. 2 cosine theta d theta. This thing right here, 4 minus 4 sine squared theta, becomes 4 cosine squared theta, and you have to take the square root of that. 8 sine cubed theta d theta over, you'll have a square root over here of 4 cosine squared theta, and you can figure that, it's not hard. And 2 cosine theta d theta. This will give you 2 cosine theta and it'll cancel out entirely with this. You're basically left with this. 8 integral sine cube theta d theta. You can look at it in this form. 8 sine theta sine squared theta d theta. You can look at this sine squared theta in terms of the trigonometric identity, the Pythagorean identity. Sine theta into 1 minus cosine squared theta d theta. And you can separate everything out over here. When you separate everything out, you get this 8 sine theta d theta. You have a minus here, everything will separate around all of that. You'll have 8 sine cosine squared theta d theta. You can do polynomial substitution over here. U is equal to cosine theta, du is equal to minus sine theta d theta, and then d theta is equal to minus du over sine theta. And plug it in here, in this right here, and see how everything changes. 8 sine theta d theta, nothing done over here. This minus and this minus will become positive. You get 8 sine theta u square sine theta du over sine theta. These sine thetas will cancel out. You basically have 8 sine theta d theta plus 8 integral u squared du. You have to take everything to completion, and we will. The integral of 8 sine theta will give you minus 8 cosine theta. Integral of this will give you plus 8 u square, which is u cube over 3. U cube over 3. But what's u representing here? U was here representing cosine. Cube theta plus c. But we have to make our answer meaningful with regards to this right over here. And let's do it. Theta over here is equal to arc sine x over 2. Plug that in places of these theta and you'll be done. Your final answer will be this. Minus 8 cosine arc sine x over 2 plus 8 over 3 cosine cube cosine arc sine x over 2 cube plus c. That'll be your final answer. If you want to make your answer even more meaningful, you could with regards to the triangle. If you do a triangle over here and you look over here, theta is equal to arc sine x over 2. Here's my x, here's my 2. What does this become? 4 minus x squared, root of 4 minus x squared. You can plug out the information from right over here and plug them in here and make your answer slightly more meaningful. Cosine of arc sine x over 2 is this, root 4 minus x squared divided by 2. You get minus 8 into root 4 minus x squared over 2. I'm just getting the cosine of this value. The cosine of this value is root 4 minus x squared divided by 2. That's this part. Then I have 8 over 3. And the cosine of all of this is going to be, and we'll present our answer in this. It'll be the cosine root 4 minus x squared over 2. But it was all cube, because we happen to have a cube right over here. Play out. Plus c. You can even open these things and simplify them. You see this 2 and this 8, it simplifies into a minus 4, then root 4 minus x squared. This whole simplifies into that. You see this 2 over here, it'll cube with that, you'll get an over 8. This will cancel out with that, because this will become a 2 cube, which is an 8. You'll essentially get this right here. This 4 minus x squared in the radical will become 4 minus x squared to the power of 3 over 2. I'm opening up the radical. 1 over 2 times 3 is 3 over 2 divided by 3 plus c. And that right here will be your final answer. So there are multiple ways you can represent same types of things, especially when you bring this into the picture. But you can work on all of this and see and confirm if it works with all of that. You could put an over 1 over here and get a common denominator into play too if you wanted. Anyhow, that's the end for this video. I hope you enjoyed this video. I know it was very complicated, perhaps, and there were some parts which were easy. And this right here is basically trigonometric substitution in a overview. I'm saying overview because you can get quite in depth with all the other different techniques that come into trigonometric substitution. It's a matter of preference here if we actually get into those or if we just keep it at this level, because this right here is a practical level. Getting too much into it, you sometimes end up losing the practicality in it, but then you also end up learning more techniques. But this was it for this video. I hope you enjoyed it. Stay tuned because I have other integral videos on the way. Thank you for watching. Have a nice day. Bye.